The voltage that appears across the positive and negative poles of a battery is called terminal potential difference. Terminal potential difference. And potential difference is often written as just PD in short. In the last video, I have shown how, because if there is internal resistance in the battery, the terminal PD across the battery, when it is connected to an external resistance, the terminal PD could actually be less than the battery voltage, which is properly called the EMF. Represent this by E. So this is EMF, the electromotive force. The terminal PD would be smaller than, say, the 1.5 volt on the battery, because some of this voltage is taken up by the internal resistance. Now what I want to do in this video is to try and calculate the power that is used in pushing current through this external resistor. When current flows through the external resistor, the electric energy would be converted to heat energy. Unless it's a light bulb, then there will be light energy, or with some other devices, then there could be, for motor, there could be kinetic energy, and so on. In any case, for this example, we just take it to be a simple resistor and assume that some heat is given out. Just heat will be given out by pushing current through it. Now, to calculate the power, let me recall what I have went through in the earlier videos on electric power. We have seen the formula P equals to voltage times current. So if I'm interested in the power converted, say, in the resistor, the voltage here would be the voltage across the resistor, which is the same as the voltage across the battery. Okay, since along the copper wire, there's very little change in potential because the resistance is very small. I'll talk more about this later on. And I, of course, is the current going through this resistor. Suppose that I call this R. I represent the resistor value by R. Then, if we use Ohm's law, if we make use of Ohm's law, that V is equal to IR, I can write this in another form. If I substitute IR into the V here, I get I squared R, or I can also make I the subject. If I move R over, I is equal to V over R. And if I substitute this into the I here, I'll get V squared over R. So there are these three forms, or these three formula that I could use if I want to calculate power, depending on whether I know the voltage, current, or resistance. So for this example, we know the EMF, we know the internal resistance, I'll call that R. We know the external resistance. So I want to calculate the power now on this external resistance. Now, looking through this formula, we need to pick one that we can use. VI, okay, the V and I would be the voltage and current across the resistor, and we know neither of this. Okay, we know that the EMF is 1.5 volts, but that's not the voltage across the resistor, because some of that 1.5 was taken up by the internal resistance, and we don't know the R yet. So we just know the resistance. So we must find at least one of these. Now let's say I use this last formula. Then I must first find the V across this resistor, which is the V2. It's the V2 that I need to find. Now in the previous video, I have shown that the ratio of V2 to V1, ratio of the voltages of the external to internal resistance, right, of the two resistances, ratio must be equal to the ratio of the resistances themselves. Now let me quickly write down the reason again. The reason is because across, say, the internal resistance, let's say I have V1 is equal to, according to Ohm's law, I times R. I times the internal resistance. That's when I apply Ohm's law to the internal resistance, little r. Ohm's law applied to the external resistance will give V2 is equal to I big R. So if I divide this, I'll get V2 over V1. Let's say I divide the second by the first equation, and that will be equal to this over this. Now the I and I cancel, so I'll get big R over little r. So they are in the same ratio. Right? When I divide this, I get this. Now this allows me to calculate V2, because if the EMF is divided according to the ratio of the resistor, then we know how to calculate, say, V2. Right? V2 and V1 is in this ratio big R to small r. So if I know, I also know that the EMF is equal to the sum of the separate voltages V1 and V2, for the simple reason that EMF is the work done to bring a unit charge around the circuit, and V1 and V2 are the separate works done in the separate resistances, as I explained in the last video. So this just means that the total work done is equal to the separate work added together. Okay, so that's all there is to it. So therefore, okay, using exactly doing it in exactly the way that I did in the last video, I should have V2. I should get V2 by using this ratio. I simply take it, first adding together the two parts, the big R and the small r in the ratio, using this ratio, and I take R, big R, over this sum, okay, and then I would multiply by the total of E. So this is essentially doing the same thing that I did in the last video, but I've just written it out in algebra. And if I do that, I'll get the same answer as I got in the last video, which is 6 over 3 plus 6. That's 6 over 3 plus 6. Plus 3 for the letter R times E is 1.5. So that's the value for V2. Once we know V2, which is the voltage across the external resistor, we can then use this formula to find the power. So therefore, the power in big R is equal to, according to this formula, where V is now V2, I should have V2 squared over big R. So using the values of 6 from there and this value from there, okay, I can find the answer to this using my calculator. The answer is 0.167 watts. That's the units for power. Okay, so let me just make clear what I'm doing. The V2 comes from here, that's the V2, and the R comes from there. So the R here is the 6 ohms. Okay, so that's the power that I get. So that is what we can get using the formula for power, and using this relation that V2 and V1 are related in the ratio of the resistances. Okay, which is why we can calculate V2 in this way. Now what I want to do next is to think about how this power would change. How would this power change if I change R? If I change the resistance. So to make it quite clear how power and R and this resistance are related, I can combine those two formulas. So let me do that first. If I combine the two formula, I can do it by just substituting this expression for V2 into here. Now the purpose of doing that is to have a formula that tells us directly how the power is related to the resistance. Right? It's not so obvious here because in this formula we see the resistance, but V2 actually also depends on the resistance big R. So to make it very obvious, let me put that into here. Okay, so that would be R over R plus small r times the E there. So this goes into the V2 there. So that means I need to square it. And then I must divide by the R. Divide by R. That looks complicated, so let me simplify this a little bit. On the top of this fraction, I have an R squared. So the R squared will cancel with the R at the bottom to give just R. And the E there is E squared. So that's a constant value. Put here E squared. And at the bottom here, I get R, big R plus small r squared. So over, okay, better put this up here, E squared, and then over big R plus small r squared. So now I have a formula. I have a formula that allows me to calculate the power for any value of big R. Right? We know that E is 1.5, that's fixed for the same battery. Little r, the internal resistance, is 3 ohms. That's sort of roughly fixed. It might depend on the current, but it's roughly fixed. So I'm just going to assume that to make things simple. And the only thing that would change, therefore, is the big R if I change to another resistor. So we have already seen that when the big R is equal to 6, in this example 6 ohms, if I calculate this formula, I would get this answer, 0.167 watts. Now what I like to see is find out is how this power in the resistor, which I shall call the output power, in the sense that this power comes out of the battery, essentially, right? It's the electrical power that goes out from the battery and get used up here and changed into heat. So I would call this the output power. How would this output power change when the resistance changes? So I could simply repeat the initial steps to find the power, or I can just substitute directly into here and use my calculator to find some answers for various values of R. So that's what I shall do. Let me show the answer directly on a graph. So suppose that I've calculated some values of the power for some values of R. And now I want to plot a graph of that. So that this is big R and that's the power. And power is in watts. Big R is in ohms. Now what we have found is a value when the resistance is 6 ohms. And the power is 0.167 as we have found. So that's 6 ohms and the power is 0.167. So that means that I can plot a point here. Now if I change this value to say 3, if I change the resistance to say 3 ohms, somewhere there, and do this calculation, I would find 0.188 watts. So the point would be here. If I change to 1 ohm, if I change the resistance to 1 ohm, then this calculation would give me 0.141. So I get a point there. I can repeat this for a few other points. What I would find is a graph that looks something like that. If I try to sketch this, it will look something like that. So it'll be a curve, and this curve has a peak. Okay, the peak is here. Now if you do this calculation, you'll find that the peak happens at a value of the big R, at a value of the external resistance that just happens to be equal to the internal resistance. You see, the internal resistance is 3, and if you plot this graph, you'll find the 3 here. And you'll find that you can actually show mathematically that if you have this function, you can use calculus, if you learn that, to differentiate this, the power P with respect to big R, and you'll find that this function has a maximum when the big R is equal to the small r. So we have an important result here. Whether you try it a few times using a graph to convince yourself, or whether you actually prove it mathematically, we'll get this result. We get the result that the output power is maximum. When now I call this the load. So by load, it just means the same as this external resistance. You think of it as load in the sense that it's something that you have to do work against. So the electric current is doing work against this external resistance. When the load is equal to the internal resistance,